So the Big Bang is really all about cosmology, which cosmology is really just the study of the origin, present structure, evolution, and future of the universe. So cosmology is a big scale astronomy. Now, the Big Bang is a really great model because it successfully explains a lot of different phenomena. The three primary ones is it explains receding galaxies by redshifts of those distant galaxies. It also explains the cosmic background radiation, the CBR, as remnants of radiation left over from the Big Bang explosion. And thirdly, it also very accurately explains the specific abundance of hydrogen and helium in space. And we're going to kind of go into detail on these three things. Specifically, what redshift is and what the CBR is. So first off, let's define galaxies. Galaxies are essentially just islands of stars that make up our universe. So this is where like stars tend to cluster together, because again, stars all tend to be born out of similar like clouds. And here are some examples of some really famous galaxies other than our own galaxy. This one here on the far right is the Whirlpool galaxy. It's a really beautiful like side-on view of a spiral galaxy. And this one in the middle is the Barred spiral galaxy. They call it a Barred spiral galaxy because instead of having just like one circular point in the center, its center is kind of elongated. But it still has like spiraling arms coming out. And then on the left is perhaps one of the most famous galaxies, and that is the Andromeda galaxy. The Andromeda galaxy is also an example of a spiral galaxy, similar to the Whirlpool. We're just not looking at it from the same, kind of angle. And the Andromeda galaxy is the closest galaxy to our own. So once we start talking about galaxies, we've got to talk about Edwin Hubble. Edwin Hubble was the first guy to realize that a lot of these images that he was seeing in his telescope were not just stars, but whole galaxies beyond our own. Because for a very long time, we thought that the Milky Way galaxy, like this was the only galaxy. That was all there was in the universe. Until Hubble proposed his idea that galaxies were way farther away than what we thought they were. And he measured their distances using what are called Cepheid variables. So they are variable stars that dim and brighten by a very specific amount, and they all do it the same way. So if they all are, dimming and brightening the same way, you can use their relative brightness to determine how far away things are. And so this brings us to redshift and blue shift, which is just a specific application of the Doppler effect, if you've ever heard anyone talk about that before. So if an object is emitting light, right, it's emitting it as waves. Now, if that object emitting those waves is moving, depending on whether it's moving towards you or away from you, those waves will either get stretched or compressed. So if an object is moving away, the wavelength gets stretched out. And so if it's visible light, the color gets redder. The opposite happens if the source emitting light is moving towards you, the wavelength gets compressed, and if it was visible light, it would get bluer. It's the same thing if you've ever experienced, think about like a fire truck or a police car with its siren on. When it's moving towards you, the pitch sounds like it's getting higher and higher. As it moves away from you though, the pitch sounds like it gets lower and lower, because the sound waves are getting compressed or stretched, just like light waves can. So when Hubble started to do his very detailed measurements of like the spectra of these galaxies that were far away, he realized that all of the galaxies had their spectral line shifted towards the red end of the spectrum, which told him that all the other galaxies were moving away from our own. And he could even tell how fast they were moving away, because the more red shifted it was, the faster the galaxy was moving away. So Hubble was actually able to measure this and put it into an equation where he was able to see that there was a correlation between the distance, how far away a galaxy was, and the speed that it was moving away at. We're not going to worry too much about the specifics of the equation because we're not going to do any calculations with it. But it is useful to look at this graph that was created from it. So our horizontal axis here is the distance that the galaxy is away from our own. And then the vertical axis is its velocity, how fast it's moving away. And you can see that there is a pretty strong correlation with several different Hubble constants. So what this meant is that if all the galaxies are moving away from our own at different speeds, that means the whole universe itself must be expanding. And this was a pretty radical idea at the time, because before that, people assumed the universe was completely static and unchanging. But Hubble showed that the universe itself was actually expanding, which got other people thinking. If the universe is expanding, if you kind of wind back the clock, right, throughout the history of the universe gets smaller, right? So what that means is that there must have been a beginning to the universe. And so George Lemaitre was the first person to kind of propose this idea of, that the universe began with an explosion. And he kind of described it as an explosion of a primeval atom. But his model was later improved by George Gamow and a lot of other people who proposed that a lot of the elements that make up the universe were actually first forged during this hot, dense stage. Specifically hydrogen and helium and lithium to a lower extent. And it was not actually these guys who came up with this model that called it the Big Bang. It was actually the people who opposed this model. The people who opposed it gave it the nickname the Big Bang, specifically Fred Hoyle, and the name was catchy, and so it ended up sticking. But the Big Bang model, especially when it was first proposed, was opposed by Fred Hoyle and others who preferred a different model. They preferred what's called the steady state model, where basically the steady state model says, okay, we concede that from the data, we can definitely tell the universe is expanding. However, the universe is going to maintain a constant density. So what that means is as galaxies spread out, new galaxies are just going to be created in the voids. So that while the universe is expanding, the density of the universe stays the same, and so there really isn't any beginning or end for the universe. However, the steady state model was disproved on several accounts. But the biggest thing that disproved it was the discovery of the CBR, the cosmic background radiation. And the cosmic background radiation, sometimes called the cosmic microwave background radiation, was actually discovered 100% by accident by Arno Penzias and Robert Wilson, who were working for Bell Laboratories at the time. And so their job was to take this really big, new, like radio dish, radio transmitter and receiver, and to fine tune it, right? They had to get this brand new cutting edge piece of equipment, fine tuned and totally working. And as they're doing this, they keep picking up noise. Like they keep getting this consistent noise in their data. And so they start going through all these processes. You know, they make sure that the dish is clean. They make sure they keep birds away from it. And they keep trying and trying to eliminate this noise, but it's still there. Until finally, it dawns on them that maybe what they're perceiving as noise in their equipment is just a natural part of the universe. It's just a natural background signal. And that's where the CBR comes from. Is suddenly they realize that this background radiation that's isotropic, meaning it's the same in all directions, probably was actually something significant. It corresponds to a temperature of like 2.7 kelvins, so very, very cold. But it matched pretty well with what people were predicting you should find as radiation left over from the Big Bang explosion. So the whole model for the Big Bang was originally developed purely through mathematics, and then we started finding evidence that supported the mathematical model. And this was
still theory?
What?
Isn't it still theory? Like it's not 100%?
Well, so here's the thing with the term theory. So theory in science and theory the way we use it in our everyday speech does not mean the same thing, like a lot of scientific words. Like when we use theory like in our everyday speech, we kind of use it like the term hypothesis, like it's something that's not totally proven or, you know, might be true. But in science, a theory has as much weight as a law. They are equally proven and supported with evidence. The only difference is that a scientific law always represents a mathematical relationship. So like, you know, Newton's laws of motion are representing mathematical relationships that you can calculate. A scientific theory, however, explains a phenomenon. So a law is always going to be related to some kind of specific equation, but a theory is an explanation. Like atomic theory. Nobody's going to argue anymore that atoms don't exist. We know they exist. We call it a theory, though, because it's an explanation of how matter interacts with itself. Just like the Big Bang is called a theory because it's an explanation of how the universe came to be. But nowadays, it's thoroughly supported and accepted as the best explanation we have for the beginning of the universe. Now, specifics about the Big Bang may change over time as we continue to get new information. That's something that is true of theories. They get adapted and modified over time because as time goes on, our instruments get more and more precise and we're able to make better and better measurements. But it is totally accepted in the scientific community. It has large amounts of evidence that back it up. Historically, though, the cosmic background radiation was the first piece of evidence that really was like, hey, the Big Bang model is probably the correct one. And we'll be talking about some more evidence that also supports it. So one of the first things that people did after the cosmic background radiation was discovered is they put together a probe to measure it more in depth. It was called the Cosmic Background Explorer, or COBE. And like I said, it was the first one. It's not even the most recent ones that we've made. We've made even more detailed maps of the cosmic background radiation. But even this first one was able to measure fluctuations in it by just millionths of a degree. And so what you essentially got was you got a heat map of the early universe. So this is what it initially looks like. But then you've got to kind of filter out some different things due to the motion of Earth through space. And once you account for that, you're going to get this secondary image right here. But again, this has got like a big line through the middle because that's where the plane of the Milky Way galaxy is. And once you kind of remove that and you've accounted for our own galaxy, this is kind of the final image. And you can see that it's basically a heat map of the early universe, where stuff in pink is just a few millionths of a degree hotter than the stuff in blue. But these tiny variations were actually very important because it was these tiny variations in temperature that actually led to, galaxies being formed today. So these tiny differences in temperature lead to like kind of the spread of galaxies that we have throughout the universe now. So here's kind of some more things that supported the Big Bang Theory. So the expansion of the universe, for one thing. Few other models take into account or explain why the universe is expanding. The cosmic microwave background radiation matches our mathematical predictions for the Big Bang very, very well. The Big Bang is also able to predict the relative abundances of elements, specifically hydrogen, deuterium, helium, and lithium in the universe, because the Big Bang created most of those elements. And I know what we're talking about is probably kind of vague, and that's because it is extremely high-level mathematics that is used for predictions on things like the Big Bang and black holes and stuff. So we would need a whole other class to talk about that before we could really talk into the details of exactly how we know all of these things. So this also allows us, if we, once we know that, yes, the universe had a beginning, that means we should maybe think about how old the universe is itself. So you can start by extrapolating backwards from the current expansion rate. So you use your Hubble constants and you kind of like work backwards and figure out, where the Hubble constant brings you to 0 on that graph, essentially where the y-intercept is. And it turns out that's anywhere from 10 to 20 billion years old. So kind of a big time span there. If you want to narrow it down some more, you can do that by looking for the age of some of the oldest stars we could possibly find. These are usually in globular clusters, like the globular cluster M10. And so that allows us to narrow down that range of time for age of the universe from more like 11 to 18 billion years old. And over time, with different measurements, we've been able to narrow it down even more. And so the current best estimate for the age of the universe is 13.4 plus or minus 1.6 billion years. So about 13.5 billion years old. Now, there was initially some problems with the Big Bang model. There were some things that it couldn't fully explain initially. So particularly flatness, horizon, and smoothness. So why does the geometry of the universe look like it's almost perfectly flat? Why is the universe so isotropic? Why does it look the same in every direction around the sky that we see? And then again, smoothness. Why is the universe so homogeneous? Why isn't there like distinct different clumps of areas that look very different? Because as we view it from Earth, the universe looks pretty much the same in any direction. Fortunately, modifications to the Big Bang Theory were made, and we were able to explain these things through the idea of inflation. So Alan Guth came up with the idea of inflation. And basically what he said is really early on in the Big Bang, just 10 to the negative 35th or 10 to the negative 32nd seconds. So like not even the blink of an eye. Just a really, really short time period after the Big Bang, the universe expanded really rapidly. So it didn't have this smooth, even expansion. It had a quick, early, rapid expansion. And it expanded by like a factor of like 10 to the 50th. So it went from being essentially smaller than an atom to bigger than a galaxy in just unimaginably small fractions of a second. And this was driven by the vast amounts of energy released during a symmetry breaking phase, which is related to some fancy particle physics. But the idea that the universe went through a huge expansion very, very shortly after the Big Bang really helps to explain the problems of flatness and isotropicness, the sameness looking of the universe. So basically, even if the universe started out in like a spherical shape, if it went through a huge expansion, the more it expands, the more it's going to look the same from our perspective. If you think about it, if you have a balloon in front of you, right, like you can tell that it's round, but the more and more you zoom in on it, like in a picture, the flatter it'll look. For example, we know the Earth itself is a sphere, but if you walk outside, the ground looks relatively flat, right? But that's just because our perspective is really small compared to the entire Earth. Same idea with the universe. Something similar with the fact that it looks the same in all directions and it seems really homogeneous. So without inflation, we would see these different patches of the sky that all kind of look different and are differently arranged. But if the universe expanded really rapidly in that early parts of the Big Bang, that means just one small part of the universe got really huge and blown out. So it would make sense that we can only see that one bubble of the universe that we're in right now. So here's kind of like a brief overview of the timeline of the universe when we're talking about the Big Bang. So the Big Bang begins right here. Inflation happens really, really quickly. Then for a period of like 1 second, you have just kind of this soup of matter and radiation and subatomic particles. And then after 1 second to maybe not quite 300,000 years, you get primordial nucleosynthesis. So this is when the first nucleuses and the first atoms are actually forming and being created. Then at about 300,000 years, the universe is starting to become transparent, right? Things are starting to separate out into distinct atoms and starting to spread out. At about 1 billion years, you get the first galaxies forming. And then, 12 to 15 billion years, this is where we get the universe as we observe it today. And this goes into more in depth on the particle physics, which I'll admit was not probably my strongest part in college. Particle physics is really confusing, but it's also simultaneously very interesting. So that leaves us with we've talked about the Big Bang as the beginning of the universe. Now we can kind of talk about the end of the universe. What is it going to look like? There's kind of 3 trains of thought, and we're going to talk about each of them, and then we'll talk about which one scientists typically agree is most likely. So there's the idea of an open universe, where the universe is just going to continue to expand forever. Then there's an idea of a flat universe, where, yes, the universe is expanding right now, but at some point it'll reach a leveling off point. And so then it won't expand anymore. And then there's the idea that, yes, well, right now the universe is expanding. At some point in the future, it will start contracting and all crunch together in kind of like the opposite of the Big Bang. Now, the idea of a flat universe can almost be entirely ruled out because scientists have determined that not only is the universe expanding, but it's speeding up. It's expanding faster and faster. So the idea that it's going to level off and stop expanding at some point doesn't make a whole lot of sense. Now, whether it'll recollapse or not typically depends on how much matter there is. So do galaxies have enough gravitational pull to kind of collapse things back down again? Now, the density for the universe to recollapse is like 4.5 times 10 to the negative 30th grams in a cubic centimeter. Observed luminous material, so like stars and galaxies and stuff, that accounts for a density of like 3 times 10 to the 31st. So that in and of itself is not enough to make the universe slow its expansion and recollapse. But there's probably about 10 times more matter in the universe than what is actually observable. And this is what we call dark matter. So the universe is pretty close to the threshold where it could recollapse. However, most scientists think that just continued expansion is more likely. But the idea that it could recollapse is not entirely ruled out. Now, what precisely dark matter is, we're not entirely sure. There is a lot of predictions in particle physics that say it could be a new type or class of particles that we just haven't discovered yet. The problem with that, though, is that scientists have been looking for a really, really long time and still have not discovered any of these particles. Some dark matter could be made up by black holes, but not all of the dark matter that we know should be out there can be accounted for by black holes. So it's still a mystery. And I'd love to be able to show us this video on dark matter, but it looks like we probably will not have time for it today. So we will wrap up with what would happen if the universe recollapsed or if it continued to spread out forever. If the universe is able to recollapse, that means as things start to get closer and closer together, it's going to get hotter and hotter. About 70 million years before the big crunch, when it would all recollapse, the temperature of the sky would be greater than 300 Kelvin. So already getting really hot. About just 1 million years before it, the sky temperature would be 3,000 Kelvin. So we're talking a night sky that's as bright as our sun. And 3 weeks before it would be like 10 to the 6 Kelvin. And then it would just get even hotter, like 3 minutes before it totally collapsed. Sky temperature would be like 10 to the 10th Kelvin. That's a 10 with 10 zeros after it. So it is, the big crunch has us kind of ending in a giant universe fireball. If the universe expands forever, it's the opposite. So in 10 to the 12th years, stars will run out of hydrogen, and that's going to leave just white dwarfs, neutron stars, planets, and dark matter in the universe. In 10 to the 27th years, most matter and objects will have already been pulled into supermassive black holes. And in 10 to the 31st years, most galactic black holes will have come and merged together to make supergalactic black holes. In 10 to the 57th years, regular, smaller scale black holes will have kind of evaporated because they'll have absorbed all the matter that they can. In 10 to the 97th years, galactic black holes will also evaporate. They will have kind of consumed all the matter that they can. And then in 10 to the 100th years, even the supergalactic black holes will have evaporated. So if the universe expands forever, essentially all the matter and energy in the universe will get so spread apart that you're not going to see any kind of meaningful change taking place. But again, this is gonna happen in an unimaginably long time from now. And that wraps up our discussion of the Big Bang.